Hello and good afternoon, everyone, and welcome to our Wednesday with Wing webinar. This meeting is recorded, just thought I would let you all know. And if you feel like you want to, please do put your cameras on so that we can make it more of an interactive session. Today, we're really lucky to have Jeanette Hagan, who is going to present to us on Projekt THERMO. It's a really exciting project. And Jeanette is an American geologist who's living in Switzerland with her spouse and 3 children. After earning a BS and PhD in California, mapping and hiking in the Sierra Nevada, sounds awful, she spent over a decade in Houston working in the hydrocarbon industry in a variety of subsurface interpretation roles with an emphasis in seismic interpretation and 3D visualization. In 2023, she joined the ZeroGeo team evaluating the subsurface potential for electricity generation using geothermal heat, including hot dry rock technology. So I'm going to pass on to Jeanette. If you have questions, please put them in the Q&A, or at the end of the talk, feel free to turn your mics on as well and we can have a discussion. Thank you. Over to you.
Thanks. Hello, everyone. I see some names I recognize, which is fun. So today I'm going to talk about developing hot, dry rock geothermal opportunities using advanced geophysical exploration methods in the Lower Saxony Basin, Germany. It's going to be a little broad, but I also want to spin because this is kind of a wing, and I know we have a lot of younger people in the group, so I'm going to spend a few minutes kind of introducing myself and talking a bit about my career path. So this career path looks very linear, right? Because it's got a big red line across it, but in fact, it doesn't feel that way at all. I grew up in North Carolina. I left there when I was 18, moved to California where I did my undergrad and my graduate degrees. My PhD was actually in volcanic stratigraphy. So I got to look at where volcanic rocks were deposited relative to the basement rocks and what that could tell us about the depositional history and what the environment used to look like 10, 20, 30 million years ago. What that meant for me was I got to go hiking in the Sierra every summer for a couple of months, which I really enjoyed. And I do really like the fieldwork aspects of geology. And I think it's really important to kind of go out there and see the rocks that we're talking about that exist in the subsurface, but we can see in reality. In between kind of my undergrad and grad school, I did take a couple of years off to travel. I really, really love to travel. At the end of my PhD, I debated going into academics or into industry. And in 2008, I had an internship with ExxonMobil. And I really enjoyed it because I got the chance to interact with, like, everywhere you look, there's all these really smart geologists who know what they're talking about, who you can learn a lot from, who are addressing really complex geological questions. And then the other thing was, in my PhD, I'm doing this work and you're coming up with ideas of what you think is there, but you can't really test it, right? In oil and gas, it was like, oh, but we can drill a well and we can see if we're right. And I was like, oh, that sounds really cool. And so when I finished my PhD, I had a job offer and decided to move to Houston and start with Exxon. I was with Exxon for over a decade in a variety of roles. I call myself a generalist geologist with a specializing in seismic interpretation. And if you look at some of the various roles that I had at Exxon, I was looking in deep water stratigraphy on the research side, actually at the research lab, and that was doing seismic interpretation. I actually was on a project, on a strat trap prediction project, if we could better predict where we could find strat traps. This was shortly after the discovery of Liza in Guyana. I got to work in the Sergipe Basin, offshore Brazil, again, deep water clastics. So I did specialize a bit in deep water clastics. And I got to use some amazing tools to really visualize the subsurface through various 3D visualization techniques. On the other hand, I also worked on a software development team and did some more of that as a quantitative interpretation specialist, using advanced softwares to try and, again, visualize the subsurface. Now notice I don't just have on here kind of each individual project that I worked on, because that's only one part of life. The other part of life is like, what happens outside work. And so I've got in green a couple of really great moments. So my wedding, I have 3 kids born at different times. And when I came back to work after the first 2 kids, I came back, I took various leaves, about 6 months the first time, almost 7 or 8 months the second time, because Exxon had instituted a 8-week paid parental leave that was lovely, that both my husband and I were able to take advantage of. And then when I did return to work, I came back part-time. I found that part-time was very difficult because you're missing out on things. People are in the office and you're not there one day. Maybe you're trying to do some work from home. And it was hard to find the right balance. And what helped me the most was I contacted other women I knew who were part-time, either who'd been part-time or who I knew had just had babies. And I said, hey, can we have lunch together? And so I set up once a month a recurring kind of part-time lunch meeting. And honestly, these women were amazing. And we bonded together for a number of years. I still, communicate regularly with some of them because, they were in the field as well. And so we could all ask questions of like, hey, how do you respond when your boss needs this, but you don't work Fridays? Do you offer that flexibility? Do you not offer that flexibility? And just in general, like parenting questions, work questions, all of these details. And that was a really great experience for me. You'll also notice there's a few red bars in here. And that's times when my life changed drastically. My mom got sick at the end of 2016 and then passed away in 19. I was very close to her, and that had a lot of impact. And then at the end of 2020, when my youngest child was about 9 weeks old, both my husband and I were laid off, along with about 200 other geologists from Exxon. So it was in the Houston area. I mean, it was a really big event. And we're like, oh, okay, well, I guess I will be on a career break, even though I'd planned, a longer parental leave. I didn't plan for this line to be quite so skinny. And one thing that we had is my husband is Swiss. And so we had the ability to say, well, let's try something different and to move to Switzerland. We'd always wanted our kids to learn German. They had Swiss passports, but we wanted them to know what it meant to kind of what their Swiss ancestry meant. So in the middle of 2021, we, after months and months of packing stuff up, we moved to Switzerland. During this time, I kind of started up a consulting firm, and I did a little bit of work because it was really important to me for my brain to be active and to be thinking about geology. So I actually got to be a visiting lecturer at a small university in California. I did a few small consulting jobs. And then with the move to Switzerland that was hard. I understood childcare in the US. I didn't understand childcare in Switzerland. And you have to figure it out. And so after the first year or so, we were better able to figure the system out and figure out what worked for us. And so I was able to start taking a few more jobs, and then got connected with ZeroGeo. And during all this time also, I had spent a lot of energy trying to figure out, where do I want to go next? Do I want to stay in oil and gas, or do I want to move into greener energy, or so looking at geothermal, looking at CCS. CCS really interested me because of my seismic background. Is there some seismic data that I can interpret so we can understand where to store the CO2? But I was also very open to geothermal. And so when John Ashbridge from ZeroGeo reached out to me, I was like, yeah, this sounds great. ZeroGeo is a Swiss-based company, and I am located here in Switzerland. And I was thrilled to be able to utilize my skills and move them into the geothermal industry. So let's talk a little bit about ZeroGeo. So ZeroGeo Energy is a leading independent geothermal development and production company here in Europe. It was founded in 2021 to develop geothermal storage and baseload electricity projects by deploying next-generation geothermal hot, dry rock technology. So we're not talking traditional hydrothermal, we're talking hot, dry rock technology. We're implementing this strategy through THERMO, which is our European subsidiary. that's actually working on developing Projekt THERMO. So Projekt THERMO is our project in Germany that I'll be talking about today. That's geothermal storage and baseload electricity generation. We also have Projekt THERMO, which we're working toward developing in Switzerland. And then we have collaboration with Eden Geopower. So this is not the Eden in the UK. This is an Eden in the US called Eden Geopower Incorporated, and it's got an electrical reservoir stimulation technology. And what this does is they're actually using electricity to fracture rocks. And so you're avoiding hydraulic fracturing and any potential induced seismicity or other concerns from hydraulic fracturing, because instead you're using electrical stimulation to fracture the rocks. It's a really interesting technology, one I'm not really going to go into today, though. I have an oil and gas background, right? So I understand the exploration and production cycle. You've got a basin where you don't have a ton of information about, so you have a lot of risk. And as you start to learn about that basin and to really delve deeper into the geology of the basin, you're adding more data and you're reducing your risk. However, once you drill a well, once you've drilled a few wells for your appraisal, your development stage of your oil and gas cycle, you've greatly reduced the risk, you've greatly increased the data, but you've also greatly increased the cost, right? As you get more and more data, your costs are going to go up. In geothermal, the project developers are taking the same risks with the same costs as the oil and gas industry, because for hot, dry rock projects, we're going to have to drill pretty deep. We're not talking 1,000 meters, we're talking 150 degrees C. But we don't have the same rewards because the price of electricity isn't quite the same as the price of oil and gas. So the question that I want to ask is, how do we de-risk at a reasonable cost? And one method that we can use to do that is FTG. And FTG is full tensor gradiometry. And the tagline here is the best subsurface exploration technique you've probably never heard of. Some of you may have heard of it. I actually see some names of people who work in it, which is really exciting, people I've worked with. And actually, Lucy, is there any way people can turn their cameras on? Is that, because I don't see anyone with it on. And if people would be interested, I'd love to have cameras on, but if we can't set that up, that's totally fine.
Hannah, could you see if you can turn the switch that allows people to turn their cameras on, please? Thank you.
I think it should be on. So if everyone just would like to turn their cameras on, then go ahead.
Oh, okay, great, thanks. Okie dokie. Yeah, I like presenting to an audience. Otherwise, I've got Lucy's reaction. Okay, so what do we mean when what can we do when we explore the subsurface with FTG? So FTG can detect lithological changes. So we can determine the geometry of a basin, we can map carbonates or salt deposits, or even map the depth of the basement. The other cool thing is FTG will detect structural shapes. So we're looking at detecting intrusive units. We can map sand channels perhaps, and also here evaluate shallow hazards. The other thing here is FTG will detect faults. So you can FTG will we can use the FTG to map the location of faults or determine fault patterns. So these are all some really cool things that we can use FTG for to understand the subsurface. FTG is really cool too because it's airborne. Okay, so we worked with Bell Geospace. And they have an old aircraft that they fly over land with some various equipment in it that I'll talk about in a minute. And so you can really rise above these challenges. So this airplane actually streamlines the process because you're gathering data and you don't have to deal with individual landowners. You don't have to deal with infrastructure and roads because all you need is an airstrip. So you can fly over both urban areas and rural areas. You could even fly over wildlife and protected habitats, as well as transition zones from over lakes and from land onto lakes or even onto the sea. It's very cost-effective over large areas because, again, we're dealing with an airplane that's just kind of going back and forth. We've gotten our permit and we can fly back and forth. And so it's much more cost-effective, especially than a 2D or especially a 3D survey. because we can deploy this over a large area for a much lower cost than what you would expect for a 3D survey. FTG sees both kind of shallow and deep. So the FTG survey can provide high quality data for the shallow subsurface, like less than 500 meters. But sometimes seismic data, especially on land, doesn't really see all that well. It can see investigations of depths up to 4 kilometers. And then the gravimeter on board, the gravimetry data, you can use that to go even deeper. So where did this come from? What is, we're still looking into what is FTG. So FTG was a US Navy technology developed jointly with Lockheed Martin. And it was developed so they could avoid, so that submarines could avoid underwater mountains. And until about 30 years ago, it was still classified. And even today, there's only a few companies that are licensed with this technology, and there's still some countries that they can't fly over. They can fly in Germany, though. So here we've got a model of the gravitational field of the Earth. It is not a round body, right? The subsurface, the gravity of the subsurface is far from homogeneous because different types of rocks and faults and other heterogeneities create differing densities and therefore variations in the gravitational pull of the Earth. So by using gravimetry, we can measure the gravitational variations and gain insight into the subsurface geology. So this is the technique using a gravimeter. So this is what I did in grad school. We did like a little geophysics field camp, and we took our gravimeter and our magnetometers, and we walked around and we took gravitational data. And so a gravimeter is, you can imagine a weight suspended from a spring, and when the gravitational pull changes, so does the length of the spring. So now as you move up and down, that length is also going to change. That's something to really be aware of if you're flying, if you've got this in an airplane. As the airplane flies higher and lower, you're going to change the length of pull because you're closer and farther away from the land. So then you get a value for the gravitational force at a certain location. What we're talking about here, though, is a little bit more complicated. So we're actually adding this gradiometry. So this is where we're adding an orientation. So the gravimetry measurement is a single value for every measured point. FTG, on the other hand, directly measures the gradient or rate of change of the gravity field in all directions of the field and is described as a tensor. So that's why it's that FTG, full tensor gradiometry. The tensor is simultaneously measured with scalar gravity. So that's the one we were just talking about, thus enhancing the efficiency of the acquisition process. So the significance of this dual recording is that modeling capabilities are significantly enhanced. So what we can use that data for to model the subsurface, it really goes up in our capabilities. The tensor measurement of the gravity field provides a remarkable increase in the resolution of the abrupt subsurface density changes, often associated with faults, grabens, volcanic intrusions, in particular salt. So for example, we have this salt body here. The traditional Bouguer curve would come down and up, but by measuring the gradient, so the rate of change of the gravity field, we actually see, wow, there's a huge rate of change right here at the edge of the salt. Hey, that's really cool. We can, we're not just saying, oh, the salt starts somewhere between here and here, but we can really start to pinpoint the edge of the salt here. So if you look over here, this is one example of some of the ways that you can combine the different parts of the tensor in order to determine what's underneath you. And so FTG combines several gravity gradiometers, each with a different orientation, X, Y, and Z, that adds a 3D element to the system, allowing us to measure all the independent components of the gravity field. So here's a little bit more details about kind of what we see and what we measure with this tool. And if anybody wants to go into a little bit more detail at the end, I'm happy to do that. I have a strong math background, but I tend to think more visually and spatially. I'm sure there are even people in this call who would think more mathematically about what I'm describing to you. So the first is depth and density. So we're looking at the tensor, the part of the matrix that's here, that's the TZZ. So this is the purely vertical measurement. And this detects lateral density changes. So here in pink, you've got these warm colored positive anomalies indicating high density contrasts. On the other hand, in blue, these cold, cool colors, you have anomalies indicating low density contrasts. So for example, could be salt or a trough or channel fill is what you might be seeing here. Then we can also look at total horizontal curvature. And so that's where you're taking all of your different purely horizontal components and combining them. And so you're looking at curvature evident in geological structures. So we've got this anticline here that we can really start to see on the data. And you could also see the tops of fault blocks, ridges, that type of thing with this measurement or this combination of measurements. And then lastly, one of the things I've talked about is how useful this is at identifying faults. Well, again, that's when you combine your TXZ and your TYZ, which are two of the horizontal plus vertical components, and you get what's called the total horizontal gradient. Where the total horizontal gradient peaks is where you have a contact or a lineament. And so you've got these edges of geological bodies. And so you can then map these as structural faults or stratigraphic contacts, where you've got two units of differing density and you've got that contact between them. So by combining, these different pieces that you get out of the FTG, you can really begin to map the geological setting of your target geology. So I've talked a little bit about the nitty-gritty of FTG, but going back to why do we want to use FTG? So FTG can handle challenges that other data campaigns can't. As I said, the lack of infrastructure roads, multiple wildlife zones. You don't have to go and talk to every single landowner or talk to lots of different bureaucracies in order to get your permits. This can be done in many cases with a single flight permit. There are some caveats. You might need a permit to fly over military bases. But on the whole, you can go from, hey, we want to do this, to the airplane flying very, very quickly, much faster than you could, for example, if you wanted to gather seismic data. You get excellent quality data near and within cities. It's very cost effective over large areas. Now, the plane typically flies in the fields at about 80 meters elevation. So we are talking very, very low. When you fly over cities, you do have to go a little bit higher, right? But you're still only going 200, 300, possibly in 400 meters. And we did this in our project that I'll discuss in a couple of minutes. We flew over the Hanover area, a large populated city. And we are still able to get good data in that without having to be stuck to roads or having to avoid the existing infrastructure. So when I ask people when people ask, what do you do? And I say, I work in geothermal, especially here in Switzerland, one of the first things I get asked is, well, doesn't that cause earthquakes? And, there's always a risk when you're looking at the subsurface of induced seismicity. But we know in many cases how to minimize that because one of the leading causes during geothermal projects of induced seismicity is the injection of fluids under pressure into fault zones. So having an early stage FTG survey can help you identify your fault zones and identify really target in on your area of interests so that you can go into areas that avoid faults and begin to minimize that risk of induced seismicity. So what does the process look like? So you start with kind of understanding where you want to go, getting the permissions, getting the aircraft, and then Bell or one of the other providers goes and flies the plane over your area of interest. So you acquire your data, and then they go in and they process it because there's going to be a lot of noise. And some of that noise might be pipelines, it might be existing infrastructure that's affecting kind of the magnetic field, et cetera. They go and process this out. This is not part of the phase that I am as more of a generalist geologist. And then again, they start to interpret it and come up with these different, total horizontal gradient, total horizontal curvature based on all of the measurements that the machinery took. and then begin to enhance that data. And then here's the bit where I come in. So where I start looking at, so I've got some seismic lines, I have some well data. How can I start laying that FTG interpretation on top of the existing interpretation that I have? Maybe, you know, old interpretation, and how can I then start utilizing that FTG? And so this is done a bit more qualitative, but then you can actually move it into the quantitative realm. And so I mentioned earlier that you can model the data, and that FTG is really good for helping you build a subsurface model. So if you have a few key, you know, seismic lines or wells, you can actually go from from just that data, and then with the FTG, you can merge that, make that FTG into a 3D model by doing this quantitative interpretation. And I'll show you the start of that, kind of this process, in a couple of minutes. So in a nutshell, to kind of wrap up my whole, what is this tool that we think is really cool and we've utilized and think has worked well. So FTG is an airborne data acquisition technique that gives you high resolution, that's non-invasive, it's time efficient and cost effective, and can be deployed over multiple varying terrains. Compared to traditional gravity survey, you get a lot more details because you've got multiple independent data sets, extremely high near surface resolution, and then what's key is that edge detection capability. So for example, in this image, this is all from an FTG survey, but inside the yellow box is where they've gone in and done infill, where the flight lines are a little bit closer together. And so you can see how that's increased the resolution of the data relative to areas where the flight lines were a bit farther apart. So in terms of what it can do for geothermal exploration, we can map different lithologies, identify locations of faults, and begin modeling detailed shapes of the subsurface structures. So this, all told, reduces exploration risks, requires minimal permitting. You can gather the data in the cities, and all with the goal of, hopefully too, avoiding induced seismicity. The technology has been used in oil and gas and mining for decades. It's proven up and has already been deployed in Europe for geothermal exploration. So where has it been deployed? So what I'm talking about, and the work that ZeroGeo has done with Bell Geospace, is up here in the Lower Saxony Basin in northern Germany. So Hanover is right kind of where the mouse is, right there. Energy and Bell Geospace also shot 2 surveys earlier this year for about 2,000 square kilometers. Ours totaled up to about 5,000 square kilometers in total area. And then there's a planned future survey this fall that's about 4,000 square kilometers in the Hessen state, again, working with ZeroGeo. Okay, so as you know, as I just want to introduce kind of what ZeroGeo did. So in 2022, we appointed Bell Geospace to carry out an Air-FTG airborne survey in Lower Saxony. And I think it took about 3 months of flying. And so that happened in late 2022 and ended in early January of 2023. We acquired a total of 4,730 line kilometers of FTG, gravity, and magnetic data. The goal was to detect basement and overlying geologic complexity, image and delineate reservoir sequences suitable for hot, dry rock geothermal exploration, and then especially in this area, delineate salt and determine the extent of potential mobile salt to de-risk drilling. Here is the airplane that was used. This is actually an app. You know, it's just one of those like flight tracking apps that people can download on their phone. And this is the flight track for one day. I think the plane's still in the air, and this is the flight track for a different day. And you can see here, these are the east-west lines. These are 8 kilometers apart. And then here is actually a zone of infill. And so these flight lines north-south are only 1 kilometer apart laterally. Okay, so next, I hope this works in terms of the sound, because there is a video with sound. If it doesn't work, I apologize. I think we'll still be able to see the video though. So this is the airplane flying over a field at 80 meters elevation. And then the second video is actually flying near Stella at the Baker Hughes test rig facility. So you can see the rig right here as it flies right next door. Again, this is flying at only about 80 meters elevation. Obviously, if you're in a city, the flight you would need to go higher. And then another thing is in Germany, with all of the wind farms, you'll need to fly higher to avoid the wind farms there. But yeah, filming credits go to Marco Suffer, a former ZeroGeo employee, and then to some people at Baker Hughes. So why did we target this area? So we're interested in this area from a hot, dry rock exploration perspective. But there's a lot of existing data because it's an area that's been explored for oil and gas and producing oil and gas for many, many years. A lot of that legacy data, though, is either very, very old. Some of these seismic lines, I think only a quarter of them are shot post 1970. I know there's one really long line that I was trying to look at that was shot in 1946. So, a year after the war ended, there was exploration happening. Some of these wells were actually drilled in the 1800s. They're salt wells that are they're still 1,000 meters deep. So because of that, you've got varying quality data. The salt flanks in the seismic are really poorly imaged. If you want to go in and reprocess the salt or the seismic so you can better image the salt flanks, which would be doable, there's significant cost to acquire that data from the owners and then to reprocess it. In terms of the wells, a lot of logs are on paper. A lot of the wells are very shallow. So if you're targeting hot, dry rock and you need that hot rock, those wells are not going to give you enough data to really start to build a model. So the blue line is the full extent of the FTG survey. And the yellow line is the extent of where we had infill. So where instead of on our north-south flight lines, for the majority of the survey, they're 2 kilometers apart. But in this yellow zone, they're only 1 kilometer apart. And part of the reason that is here is because there's not as much data here. The purple are the 3D surveys. There's no 3D in this zone here. Okay, so what did we actually get to see when we got this FTG, and how does it compare with what already existed? So what I'm showing here is the white contour map. It's an old map. It's the Baldschön kind of German model from 2001. This has been updated, but honestly, this is the best way to look at it right now because some of the newer maps are digital and in 3D, and it's a little bit easier to see the geology here. So this is the base of the Buntsandstein. And so you can see there's a thin missing data from where the salt had moved up. And then this is overlain by this blue, which is one of the current German database maps of where salt exists. And the dark blue is salt diapirs, salt domes, and the light blue is just thick salt pillows that would probably be in the Zechstein just below this Buntsandstein layer. So we can see, okay, these two pretty much line up, and hey, maybe this is a little wider here because at a higher elevation, that salt comes up and balloons out, and so it's going to be a little bit wider here. Well, what did we see in the FTG? Okay, remember blue, as we discussed earlier, is typically where your low density rock is going to be. Salt is very low density, and so here we have what's likely more salt or thick salt. In the red sections, we have thicker sediments with probably less underlying salt. But one thing I notice immediately is there's some salt over here that isn't showing up here. Okay, we've got some faults there. Maybe that does something. And then it also appears much thinner here. I'm not seeing that same blue. So there's less salt here than I would imagine based on this interpretation. I've talked a lot about how FTG can show us faults or help us delineate faults and also help us see edges, so edge of salt. And here you can really see that. So this is the FTG with the lineaments laid on top. And so you can see here, would be the edge of salt, more edge of salt, edge of salt. These are a combination of faults or edge of salt, perhaps in here in this thick sediment. We have some faulting. We don't know yet, because we haven't modeled it, as to whether that fault would be something shallow or something deep. And that does require some modeling. But now if I go back and I say, okay, how is this different? I can lay these things on top of each other. And again, we see the same things I just pointed out. There's no salt in the previous map here, but it's definitely got a low density gravity FTG response. So this is something that I want to examine as I build my model, as I try and understand the subsurface. So how do you model it? Okay, so going back to, again, kind of where I've come in and where I focus. So I mapped this 2D seismic line. And again, we're looking at 2D modeling right now. So I've got a 2D seismic line with these two very large salt domes. I cannot see on the flanks of the salt dome or underneath the salt dome very well at all. And so, I just said I've mapped what I can in terms of the stratigraphy. Let's just say, what if this is all salt? That might not be exactly what to expect geologically, but hey, what would that look like in terms of our FTG response? So in dark green here is the observed kind of measured FTG vertical gradient. So that's what's measured by the plane, by the instruments on the plane. In the thin line here is what was modeled based on if the subsurface looked like this. And this modeling was done by Meditech. And so if we see here, the thin line goes way, way, way lower than what we actually observed. So we can determine that we have way too much low density material right here than what we see in reality. So you say, okay, toss model 1, what can I learn from it? Let's switch to model 2. So in model 2, we've actually zoomed in and we've changed the scale here. And so we're actually, even though it seems like this is the same curve, it's actually much smaller than the previous panel. And so we can start to see a bit more of the small variations in the observed, measured data. And then also we can see in our model data, because now we've modeled a thin feeder with a bulbous top, the thin salt feeder. So we've got more of what you would really picture in your head as a true diapir. So, if we were to reprocess the seismic, we would probably be able to see some of the sedimentary units extending underneath this kind of mushroom-shaped salt body. One other thing I'll point out is, this is a model, and this is a model in 2D. The FTG is measuring things three-dimensionally. And so when we see in this curve, we see like a bump here, but we don't really see any changes in this section. Maybe there's a little thicker salt in this pink section here that would help me understand why there's a drop in the gravity field here. On the other hand, it could be that there's a salt body lying just off or just a little farther away from this one 2D line that we have. And if we take this and we put this and we start creating a 3D model out of it, we're actually going to be able to start to see all of those little variations laterally and along the line of the seismic that we do have. You don't start out when you do this FTG, you don't necessarily plan on modeling the entire FTG. You might say, okay, I'm going to do a 3D model of the area that most interests me, because of course, the more modeling you do, the more cost that's going to add. At the same time, the cost of 3D modeling is still doesn't compare to the cost of acquiring 3D seismic data. So kind of to sum up here, what are the advantages of using FTG data for geothermal exploration? So FTG provides crucial information, including a model. You can create a model of the subsurface and defines hazards such as faults, fault domes, and potential shallow subsurface geology. You can get a first pass basin thickness and depth to basement measurement. You bridge your knowledge between the existing surveys and therefore improve your subsurface models. especially when you do that forward modeling, integrating additional data like seismic and offset wells. But then you can even get a potential for a first-line temperature estimate. As I've said a couple of times, the FTG excels at imaging shallow underground sections, like the top 500 meters, because these might be a struggle for seismic, especially in onshore. So FTG can be used not only as a standalone method, but as a way to enhance your existing seismic interpretation. I've talked a lot about like the cost difference between FTG and 3D seismic. I haven't given you exact numbers, but it's like this. And also by shooting an FTG over a big broad area, you can then reduce the cost of a 3D survey because you can determine the acquisition, the area and the parameters. You can define the orientation so that you get the best imaging and reduce offsets. And again, it's time and cost efficient. And I'm one of the people who, coming from an oil and gas background, if I'm going to drill a very deep well to hit that 150 degrees C temperature, I probably do want to have a solid understanding of what I'm going to drill into and would like to have the 3D seismic data as well. But once I kind of optimize my drilling location based on the FTG and my area of interest, then I have a much smaller area that I really need to focus on in terms of all the additional work that I need to do in order to de-risk that area to drill. And I believe that summarizes everything I wanted to say today, and I'm happy to answer questions. I don't know if there's any in the chat yet, but I'm happy to answer questions. And if anybody has any questions or wants to follow up after this, please let me know. I'm available on LinkedIn. I didn't include my link there just because I don't know if anybody's like going to write it down and you can't click on it, but just search my name on LinkedIn and you can message me on LinkedIn and I'm happy to answer any questions you have.
Thank you so much. That was absolutely fascinating. I was thinking through it, you must be an amazing lecturer. I was hooked the whole way. And what a great project. Does anyone have any questions? Come on, there's got to be some questions for that. That was brilliant.
There's a couple in the Q&A box, Lucy, if you want to have a read through them. Yeah.
I'll read them. Okay, great talk. Can you please share a few papers on FTG applications for EGS?
Okay, and yeah, Lisa is saying we can't unmute ourselves. Yes, can I do that right now? No. I'm some of the people I'm working with at Bell Geospace and at Meditech, I'm sure have those papers handy, and I've read a few of them, but in terms of actual applications for EGS, I'm not sure that there's many out there, to be honest, because this has not been used a ton in geothermal, and when it has been, I don't know if people are publishing yet.
Okay.
Hey, sorry, that was my question. Can you see or hear me?
Yes, we can hear and see you.
Yeah, okay, perfect. Yeah, thank you. I know I'm writing a review on geophysical methods to characterize EGS resources, and I do have a section on FTG, which is why I was.
Oh.
Is that me or her?
Her, I think.
Okay. Okay, well, Rebecca, we missed that. You cut out for a second. Do you why don't you message me offline, or unless it's something that?
Sure.
And I'm happy to we can talk through some of the things I've encountered.
Okay, thanks. Yeah.
Okay, cool. And then Liesl, you had the question about gravity and FTG.
Yeah, because I saw on your, can you hear me okay?
Mm-hmm.
Yeah.
Okay, cool. I saw on your earlier slide that I think you said for this project that you did FTG and gravity and mag.
Yep.
So I was just wondering, like, I did miss the first bit of the presentation.
Yeah, so in the first bit of, so it's FTG, I said here, FTG, gravity, and magnetic. And it's basically because they're all just on the plane. And so here you've got your basic gravimeter And
Yeah.
I have to be honest, I have not been on the plane and seen all the instruments. But all the instruments are sitting there on the plane that measure the gravity, that measure the gradiometry, so the different axes of the gravity. And the magnetic tool is already on the plane. And so when you're flying the plane over, you just kind of use all of those combined because it's kind of already included in the price.
I guess I thought, and I realized maybe now it's just probably a wrong, maybe I'm just totally wrong. I was imagining the FTG almost replaces the need for, normal old school gravity measurements because you're getting the full tensor gravity.
Yeah, I mean, I think so.
Okay.
Yeah.
So then I was just wondering, why wouldn't you not need to collect gravity data if you're already doing full tensor gravity data or gradiometry?
Yeah, that's not a question I'm totally able to answer. BelGeo would know the answer to that and be able to explain it. So sorry about that one. But I mean, so for example, this, so we've labeled this as FTG full spectrum gravity, 25-kilometer residual. So this is what the calculated kind of Bouguer gravity map would look like. But it is calculated from the FTG data. And so it's not just your pure vertical, but it's actually got a residual looking out 25 kilometers in terms of kind of what the broader impact is off into your lateral space. Because if you were doing more of a traditional gravity, you wouldn't just be seeing vertically, but you would kind of be seeing in a radius around you.
Yeah, okay.
At least how I understand it.
Yeah, it's so interesting. And I didn't write this in the Q&A section, but are you able to talk about how, what actual sort of geothermal insights you got for this project in Germany?
I'll have a few more at the EAGE meeting in a month.
Okay.
This is kind of an overview of what the technology is.
Yeah.
I mean, the big one is what does the salt structure look like? That's been the big insight. Now what's funny is there's actually a paper that came out, I think in the last 20 years, I don't remember what year it was, but it was actually using gravity measurements made in the 20s and 30s in Germany. And it looked at one of the salt domes very close to this one. And it also decided that it was mushroom shaped and could actually map out some of the shape of the salt body from these gradiometry measurements. And I think they were gradiometry, not just pure gravity, but gradiometry measurements made in the 20s and 30s that they went in and recalculated.
That's crazy.
So yeah, there's some cool stuff that you can do. There's also, there's some big faults in the area that this really helps us interpret. In terms of looking at some of the shallow versus deeper faults, that's something that I'm still curious about and we're still moving toward.
Yeah. Thank you. It was an excellent talk. Thank you so much.
We have a few more questions in the post. So great talk. Thanks so much for the inspiring intro as well. I have a question about the uncertainty of the final measurements used for the modeling. Are there some metrics that give you higher or lower confidence in the data, such as rough topography, high flight lines, etc.? And that's from Andrea.
I think the short answer there is yes. There are metrics in terms of kind of how you process the data. Unfortunately, that is not something I'm part of, but I didn't participate in that. So understanding those exact metrics in terms of confidence intervals, obviously the lower you fly, the more you're going to feel versus the higher you fly. So how do you correlate that and remove that noise as well? These are all things that are incorporated in this processing phase that Baltic Geospace did. So looking quickly at some of the other questions, there's two here about data needed to, what data is needed or helps the survey design. And this is very similar kind of what was just asked. How do you gauge data confidence based on surface terrain and infrastructure? Again, that's all part of kind of Bell Geospace has been doing this for a very long time. And so kind of has the experience to plan that out. So this is not something that ZeroGeo planned. This is planned in collaboration with Bell Geospace that's flying the airplane and understands the layout of the topography, a little bit to some extent the wind patterns and kind of how we want to design that. And then Simran asks, how are the lineaments calculated? Is it when there's a very sharp gradient change? And the short answer is yes. So the long answer is this image. So you can see here where you're going from higher density rock into lower density rock. And so your traditional gravity drops. I hope you can see this. With this, with the way I'm presenting, I don't know how to zoom in, so I apologize for that. But the red line is your traditional gravity. And so that drops as you hit this, this less dense body. And so you can see here what's called the total horizontal gradient, and that's the line in kind of dark green. So it peaks right here, right where this drops, and so right where this contact is. And so the way that they actually identify the lineaments is they take the peaks of this total horizontal gradient calculation. And so you can see here, here's where the peak is in that right along the fault here. And again, when you're looking at something where you're going from something less dense into something much denser, again, that's where the peak is here and here on the edges of that change in density. So on the contact or edges of the geologic body.
Thank you, Jeanette. It's super nice to like be listening to your presentation. Yeah, so are these lineaments? They'll only be valid in the first 500 meters, because that's how far the data goes, or the FTG.
No. So the FTG goes down to, you can see down to 4 kilometers.
Oh, okay. Wow.
Obviously the resolution diminishes, but no, we're not just looking at, hold on, let me see if I can, so here, I think that might have been a little confusing. So the FTG does see deeper. You can have two different kind of, they can balance out where they think the data is coming from. And so much more of the data is likely coming from the shallow than from the deep. But that's not saying that you can't see things that are deeper than 500 meters. You absolutely can, including faults and these gradient changes, these edge features. You can see. So especially, I'm looking forward to seeing what we see in the Rhine Graben, right? Because you're going to have a Graben boundary, so you're going to be able to see those Graben, those edge fault, those faults there on the edge of the Graben. And I'll look forward to seeing what that looks like.
Thank you.
Okay, thank you. Are there any more questions from the audience? I have one. This is a huge amount of work. Like, what's next? So you've got to have a look at the faults, and then what's the sort of game plan for Project THERMO?
So game plan for Project THERMO is kind of continuing from the subsurface interpretation side, is continuing to work the data to identify areas where our area of interest. What can we see? Really start to map out in depth some of the faults that we see, lineament features. Identify what those are. Are those faults? Are those salt contacts? Are they shallow faults? Are they deep faults? What can that tell us about our area of interest in detail? And then continue with, so we've done some 2D modeling. We want to continue into the 3D modeling world. So we can really understand the whole region or our whole area of interest better. And this will also help us identify those faults and those boundaries that we're looking for, and the depth to I mean, I'm hesitant to say depth to basement because there's just so much sediment
Yeah.
in the area where we're looking. But it's really for us here. It's about the salt and faults.
Yeah. No, great. It's so inspiring seeing all this data and what can be done from sort of a UK perspective, when a lot of the geothermal work has been done with very, very minimal data. It's been slightly drill and hope, and this is yeah, it's amazing to see what can be done with proper geophysical techniques. So I'm sure a lot of us will be taking notes away.
Great. Well, thanks for letting me chat with y'all. I appreciate it.
It's a pleasure to have you on.
And again, yeah, please feel free to reach out on LinkedIn if you have any questions or want to connect.
Thank you. Thanks again. Thank you all for coming.
Thank you. Bye.
Thanks for a great talk.
Thanks, y'all. Okay,
Oh,
I ended the presentation.
That was the best attended talk we have had in
How many
a
people?
long...
Wait, are we still recording? Let's stop recording.
Oh, yeah.
Oh, yeah. Is that me?
Can you do it?
I think because I didn't start it. Oh, no, wait. Yeah, I can.
No, it said recording started.